Hi, I am Satish Kumar. In this video, I will explain the moment distribution method to analyze a frame which can sway. I will start with the reasons for sway, then I will explain the process with an example. Sway occurs when a lateral deformation is unrestrained, or it can be due to asymmetry. Like in the first figure, the first column is shorter than the second column. In the second figure, there is a lateral load. In the third figure, we have a concentrated load which is placed eccentric, and in the fourth figure we have a lateral load. We will consider this frame ABCD with the column AB having a height of 3 meters and the beam BC having a span of 3 meters with a uniformly distributed load of 12 kN per meter, and the column CD having a height of 4 meters. For all the members, we will consider EI as a constant value. To estimate the value of the stiffness of a member, we need to look at the far end. So in the far end is a fixed support or it is a continuous joint, then the stiffness value will be 4EI by L. If the far end is an exterior hinge, then the stiffness value will be 3EI by L. In our case, all the values are 4EI by L. Only the L value for the member CD is 4 meters, whereas for AB and BC it is 3 meters. And with respect to the distribution factor for an exterior fixed support is 0, and the distribution factor for an exterior hinge is 1. For the interior joints, the sum of distribution factors must be equal to 1. The span BC alone carries a uniformly distributed load of 12 kN per meter over the entire span of 3 meters. The fixed end moment will be WL square by 12. So the fixed end moment at BC will be in anticlockwise direction. We will assume anticlockwise direction as positive for moments, and the fixed end moment CB will be in clockwise, so it will be minus 9 kilonewton meters. For the spans AB and CD, there is no exterior load, so the value of fixed moments will be 0 for these two spans. Now I will frame my distribution table. The first row will be joints, the second row will be members. So at joint A I have only one member AB, and at joint B I have two members BA and BC. Similarly at joint C I have two members CB and CD, and at joint D I have only one member DC. My third row will be distribution factor and my fourth row will be fixed moments. When we look at the joint B, the fixed moments are not balanced. So I will balance this positive 9 moment with a negative 9 moment. So that minus 9 will be distributed over B and BC in the as per this distribution factor. So 9 times 0.5 is 4.5. So here I will distribute it as minus 4.5 and minus 4.5 for each span. Similarly, when I look at the joint C, the unbalanced moment is minus 9. So I have to balance that with a positive 9. And the positive 9 has to be distributed with the factors 0.57 and 0.43. 9 times 0.57 is 5.13 and 9 times 0.43 is 3.87. After balancing, these moments will be carried over to the nearer joints. From B it will be carried over to A, and from B it will be carried over to C. Similarly, from C it will be carried over to B, and from C it will be carried over to D. There will not be any carryover operation from any fixed support to the nearer joint. And these carried over moments are also not balanced. So again I have to perform a balancing operation and I have to repeat with the carryover operation. And I will repeat this process until my required degree of accuracy is reached. Like here, the unbalanced moment, it reaches to 0.001. So I will stop with this. Then I will add up all the moments from my fixed end moment. So from this line, I will add up all the moments until the last row. And at the last row, you can see that the moments are actually balanced. At B, it is much closer to 0, and at C, it is actually 0. From the estimated values of the bending moment, I will now try to find the shear force and the support reactions. For the column AB, I am having a 6.228 moment at B, and at joint A, I am having 3.116 moment. Both these moments are acting in clockwise direction. So my reaction and the shear force should compensate this with an anti-clockwise movement. And similarly for the column CD, the moment at C and D are acting in anti-clockwise direction, so my resisting moment due to the reaction and the shear force must act in the clockwise direction. When I look at the value of the reactions obtained at A and D, my sigma fx is not equal to 0 in this case. So I will have some resultant acting. So the resultant will be responsible for the sway of my frame, and I will consider the joint C to sway by a distance of delta in horizontal direction. If I assume my beam as a rigid, then the joint B will also move horizontally by a distance of delta. From B, when I look at A, the end A is fixed, so the induced moment because of this lateral displacement will be 6 EA delta by L square. If my far end is hinged, then the induced moment will be 3 EA delta by L square. In both the cases, I have a different lengths. For AB, it is 3 meters, and whereas for span CD, it is 4 meters. I don't know the value of a delta, so I will take the ratio of these two moments. So MAB by MCD will be 16 by 9. Now these assumed sway moments will be distributed over the entire structure. For the beam BC, I do not have any induced moments because we have assumed this span BC as a rigid and it will not have any deformation, so it will not have any induced moments. When I look at the joint B, the moment is not balanced. When I look at the joint C, the induced moment is also not balanced. So I will perform the balancing and carry over operation n number of times until the net moment at B becomes 0. Similarly, the net moment at all other joints becomes 0. With this balanced induced moments, I will find the support reactions and the shear forces for the columns. And you can see for the column AB, the moment acting at A and B both are in the anti-clockwise direction. So the direction of the reaction at A and the shear at B must be in clockwise direction. Similarly, for the column CD, the moment at D and C both are acting in anti-clockwise direction. So the direction of the reaction at D and shear force at C should act in the clockwise direction. To determine the magnitude of these forces, I will distribute the sum of moment over the span. Now, when I look at the support reactions, the sum of reactions at the support CA and D, we have a resultant. Let us call this resultant as R dash. We have calculated the resultant due to the load and the resultant due to the assumed sway, which is a delta. By principle of superposition, I will find the ratio between these two resultants and find the factor for actual sway moment due to the applied load. I will add the moment due to the external load with the factored sway moment or the actual sway moment, and I will arrive at the net moment at that particular place. So when I use this net moment to estimate the support reactions, the support reaction is at A is acting towards right with a magnitude of 2.348, whereas the support reaction at D acts towards left with a magnitude of 2.349. So now our structure is complete. We can draw the bending moment diagram and the shear force diagram. To draw the shear force diagram, I will just follow the direction of force, and my sign convention will be to the left of section. If the shear force is acting upward, then that will be a positive shear force. If my section is a horizontal, then if the force acting to the top of the section, if it is towards right, then that will be my positive shear force. To draw the bending moment diagram, I will consider sagging moment as a positive for the beam, and at any joint we can see that the sum of moments must be equal to 0. So if there is a positive moment, there is supposed to be a negative moment with the same magnitude at all the joints. You can include other details in your bending moment diagram, such as the point of contraflexure, magnitude of maximum bending moment, and the location of maximum bending moment. If you have any queries, you can contact me.